Okay, and with that, I will hand it over to you.
Sure. Good afternoon, everybody. So I have two students presenting today. The first one is Cynthia Sias. She is originally from El Paso, Texas. She went to Cornell for her undergrad. After that, she came here for a master's. She will be finishing off next semester. And she got really intrigued with Johnson grass and came with sorghum. So she did a great work over the past 2 years. So here she is presenting her results. Go ahead.
Alright, thanks for the introduction, Dr. Matthew. Hi everyone, thank you all for making time to be here today. Today I'm going to talk a little bit about my thesis project that is concerned with better understanding hybridization between sorghum bicolor and sorghum halepense. So as many of you already know, sorghum is one of the most widely cultivated crops in our state of Texas. Unfortunately, it has a weedy relative, Johnson grass, which is so closely related to the bicolor that they can share genetic information with each other through a process known as gene flow. And gene flow is of concern to us because it has potential environmental and economic consequences. So an example of that would be a trait of interest going from the bicolor into the halepense. So for example, if anyone's familiar with Indian sorghum hasn't been released, but it would be an ALS inhibitor-resistant grain sorghum that would allow a close application of an ALS herbicide, killing the Johnson grass but not harming your sorghum crop. But if that trait of interest, if the resistance gene were to be transferred into the halepense, then the halepense becomes resistant and then your herbicide doesn't do anything, which is what we don't want. So that's a potential scenario as a result of gene flow, which we don't want to occur, but it is a possibility. So a little bit of background between the two species. Sorghum is a diploid with 2 copies of its chromosome, while the halepense is a tetraploid having 4 copies of its chromosome. And so when the two species hybridize, you typically have a triploid progeny. But because of the unbound set of chromosomes, there is a process called a triploid block, which tends to occur, and as a result of that, the embryo collapses and that seed doesn't germinate. However, the more we learn about this and the more we understand it, the more we realize that that's not always the case. So sometimes you'll have unreduced gametes that lead to odd ploidies. So most commonly we've seen tetraploids emerge, but you also have sometimes pentaploids, hexaploids, and we've even seen some of the triploids being able to germinate and establish out in the field. And so this is all a result of hybridization and gene flow, which is what we want to better understand. So we believe that there are 3 main factors that drive gene flow. One being the sorghum parental background, the second being the type of cytoplasmic sterility in the bicolor, and then lastly, the presence of pollen, of self-pollen competition. So those are the 3 objectives of my study. The first being to determine if the frequency of gene flow is affected by the sorghum parental backgrounds. In my case, I had 12 different genotypes. Secondly, to determine the frequency of gene flow as a result of the type of cytoplasmic sterility. In my case, I had 3 different types. I had A1, A2, and A3 type of cytoplasmic sterility. And then finally, to determine if the frequency of gene flow under self-pollen, or what that looks like under self-pollen competition. So to get us started, all of my experimental fields were located at the Texas A&M Research Farm in Flint. I had 2 main fields. So my first field was the fertile field, all of the beelines, where I had 13 different parental backgrounds. One of those was Indian sorghum. All of those 13 were replicated 4 times and arranged in a randomized complete block design. And then my sterile field had 12 different lines of parental backgrounds, all of which had A1 cytoplasmic sterility. And then on top of that, I had 3 more sorghum parental backgrounds for which I had 3 different types of sterility. So for a total of 18 different combinations. And then those 18 different plots were, again, replicated 4 times and arranged in a randomized complete block design. So This is an aerial image of my male sterile field. Each one of those blocks is a different parental background. And as you can see, for the sterile fields, we created a sorghum border that surrounded that one field to prevent any outside pollen from coming into that sterile bicolor. So this is what that field looked like from the ground. You have the male sterile sorghum in the middle, surrounded by Johnson grass, and then you can see the tall sorghum biomass border towering over that entire field. And that's another close-up. This again is an A line, a sterile line. Since you don't have bicolor pollen being produced, you don't have seed set there. So theoretically, any seed that we found on those sterile panicles was a result of the Johnson grass pollen going into the bicolor. So we were lucky enough that my fields were completely covered in Johnson grass. It was all over the place, so I had no issue having to deal with flowering symphony at all. I've never been happier to have a field full of Johnson grass, but in this case we were. So that wasn't an issue. So we let the natural population of Johnson grass go wild, do its thing, and similarly the bicolor, we just let it go throughout the season. And then we came back at the end of the season and collected 50 panicles from every single one of those plots. And so those panicles were then threshed individually using the belt thresher at Dr. Rooney's lab, and then we cleaned the seed and then counted it on an individual panicle basis. Can we close that? Yeah. Okay. Okay. So in order to confirm how much of that seed was a true hybrid, we had to grow it up and we had to put it through. So once those seeds were germinated and emerged, we then ran all of that through a process called flow cytometry. So flow cytometry tells us the ploidy of any given seedling. So if it was a triploid, if it was a tetraploid, pentaploid, or hexaploid, we consider that to be a true hybrid. So in the case of our fertile seed, we collected 300 grams of seed from every single parental background. We grew it out in progeny rows, and then we kind of just let it go, and then came back, walked those fields, and picked out anything that looked like a hybrid. Because the hybrids are kind of obnoxious plants. They're very tall, they don't look like sorghum, they have these weird panicles, and they don't look like bicolor. So it's pretty easy to pick them out. So anything that looked like a hybrid, we collected tissue and then ran it through flow cytometry, and then confirmed if it was a true hybrid or not. So similarly, for our sterile seed, we grew out that seed, but we also, as you can imagine, for our sterile seed, we had a lot less of it. So what we ended up doing was we separated that seed into two different pools. So half of it went to a greenhouse environment, and then the second half went out into the field. So again, we grew it out. Anything that looked like a hybrid, we ran it through flow cytometry to confirm. But also by having those two environments, we're also able to look at hybrid seed establishment when you have different growing environments. And I'll talk about that in a little bit. So this is what that looks like. Like I mentioned, those hybrids don't look anything like the bicolor, which allowed us to just walk the field and then visually point out what we thought was a hybrid, and then later on confirm through flow cytometry. So in order to actually calculate the level of frequency, starting off with the fertile section, we came up with a total number of hybrid seeds, then divided that number by average number of total florets, multiplied that number by 100, and that gave us the gene flow frequency under no pollen competition. Similarly, for the fertile section, we obtained a total number of hybrids observed, divided that by an average number of total plants in those progeny sections, and multiplied that by 100 to get the gene flow frequency under self-pollen competition. And so then those two pools of numbers we looked at under using proteomics using stats. And we didn't have to transform any of our data. So again, just to give you visual images, here on the left we have a sterile line that had low frequency of seed set, and then on the left we had high frequency of seed set. So you can imagine that those parental backgrounds that had the higher frequency of seed set are more likely to produce a higher amount of gene flow frequency once those hybrids were confirmed to be hybrids. So getting into the results section, starting off with the sterile section, in a nutshell, we did confirm that the genotype, the sterility, and the combination of those two factors were significant, and I'll break that down. So this is a distribution of those 12 sorghum parental backgrounds that all had the A1 cytoplasmic male sterility. So under no pollen competition, you can see that 2928 is just shy of 3% gene flow frequency, followed by 626, which is just a little bit above 2.5% gene flow frequency, and then following behind was 623, which was just above 1% gene flow frequency. So no pollen competition, A1 cytoplasmic male sterility, those are the three parental backgrounds that kind of stand out. Now, when you take into account the different cytoplasmic male sterilities, we had the three parental lines that had the three types of cytoplasmic male sterility. And so again, the one that jumps out at you is 623, which was the third highest here. But then also now you're looking at the A3 cytoplasmic male sterility. So taking those two factors into account, we see that the combination of those two factors are giving you the highest amount of gene flow frequency here. It's above 4.5%, which was the highest that we saw throughout this experiment. So now when we look at the scenario where you have pollen competition, so now these are all the B lines, which means that your sorghum is producing pollen, and then that bicolor pollen is competing with the Johnson grass pollen. So when you have that competition, I'd like to point out that on the y-axis you have an incredibly lower amount of gene flow. So here the highest was 626, and even that was only 0.035, which is telling us that self-pollen competition is substantially decreasing the amount of gene flow that's going on. And then the establishment data that I mentioned earlier, so that seed that came from the sterile field that was divided into the two environments, as you would imagine, that seed which was grown in the greenhouse had a higher level of establishment. But I thought it was pretty surprising to find that 3% of that hybrid seed was able to establish out in the field. Even with competition from other weeds and all of those environmental factors, they're still able to establish. So this is really the first detailed study of hybridization between sorghum and Johnson grass, where we looked at a wide variety of sorghum parental backgrounds. We have the three types of cytoplasmic male sterility, and then the component of the presence of self-pollen competition, and how these three factors are really affecting and driving gene flow. In the past, there have been other studies that looked at fewer controlled crosses, mostly in the greenhouse, with a smaller amount of parental backgrounds. But a study that's been done at such a scale and out in the field, I think this is the first one that I've read about and or that I've seen. And even at such a large scale, we're still seeing that the presence or the interaction of the genotype as well as the type of cytoplasm is a strong factor for gene flow. So if you snoozed off or just kind of were lost, these are the main ideas behind this project. This is what you need to remember from the presentation. It's just that we are seeing that gene flow varies across our sorghum parental backgrounds. We now know that the interaction of the genotype and the type of sterility also is driving gene flow frequency. Also, importantly, that the presence of self-pollen and the competition is substantially decreasing the amount of gene flow that we're seeing. And I think the most important thing to remember, and the thing that I like to take away from this presentation, is that we know that we can reduce gene flow. So sorghum breeding programs that, are choosing which lines to use to make new varieties. You now know that there are certain parental backgrounds that are less likely to hybridize with Johnson grass. So eventually, when you have a new variety that's going to go to a grower, we can choose parental backgrounds that are less likely to hybridize. And, in the long run, we are slowing down gene flow, decreasing the chance for resistance problems later on, and issues similar to that. So in the future, we're still running the second replication. We're still working on it. So we have to do the second replication of the experiment. We're still running samples, but hopefully by 2020, we'll have the 2 years of data that we can look at. We're also trying to learn about what these hybrids look like. And so, what does the F1 progeny look like out in the field if it's able to establish? And on top of that, do the parental backgrounds have anything to do with what these hybrids look like? That's also of interest to us. We currently have 3 hybrid nurseries out at the farm. So if anyone's interested, we can go look at them. They're kind of weird plants, but they're interesting. And then also, I think there's future plans for looking at gene flow frequency going in the opposite direction. So when you have Johnson grass as a female, what does that frequency look like? These are my references. Thank you to the sponsors and people who fund this project. So Texas A&M AgriLife, USDA NEPA, USDA ARS. All of my community members, Dr. Green, Dr. Patricia Klein, and Dr. Jessup. And Dr. Yuthi, thanks for bringing me on and willing to bet on me. And special thanks to Dr. Hodnett and Dr. Nithya for helping me out in the field. But more than anything, thanks to my lab mates, because they make work really fun. And I really like them. They're cool people. And that's all I got. So if you have questions, let me know.
Yeah, plenty of time for questions. You have 10 minutes.
Dr. Murray.
So, great presentation. The most relative thing to a grower and what's grown across most of the country is hybrids. So why did you use lines per se instead of hybrids to this experiment, at least on the sterile side or the fertile side?
I believe the idea, and Dr. Rooney, correct me if there is a better explanation, but the idea is that we're working with lines that are going to be used to develop, new varieties or new hybrids. So we're kind of like using the foundation, I guess, to better understand how the parental backgrounds end up influencing hybridization.
So let me add to it. That's a fair thing to ask. That's a fair thing to initially do. But some of the hypotheses we have about gene flow in this process are that the hybrid itself is probably less likely to be a point of gene flow than, quite frankly, derivatives of that hybrid based on where we move seed. We're talking about trucking and training seed and the types of situations where you're going to have the environment that's same to replicate Johnson grass and sterile and fertile lines that are not hybrids directly involved in each other.
From the hybrid seed production.
No, not hybrid seed production, actually the grain share. Because remember, when the farmer harvests F2 or F1 seed off of a hybrid crop, he's harvesting F2 seed, which is going to segregate for sterility the next generation of F2 seed. If you're in South Texas and you're moving seed next to grain next to feed chickens, you're dribbling it all along the meadow. It's just falling next to it. Okay? You set up a natural crossing.
And also the volunteers that come up after the harvest. So when we have Johnson grass. Great.
So that's a fair thing to do.
So what's the worry? The worry hybrid, or the worry that gene flow in Johnson grass and the fact that you could possibly end up with a herbicide resilient Johnson grass?
So the way I interpret it is that the main concern is the possibility of having traits of interest that were meant to be only for the bicolor to be transferred to the weedy relative. That's the main concern.
So, you were thinking that the gene flow is most likely going to occur from one of the naturally occurring hybrid Johnson grass.
So from what I understand, it is more likely to have, like Dr. Rooney was explaining, that F1 seed that is often, dribbled across the road during transportation. That is, kind of what we're replicating. Sorry, FTC, yeah. So that's kind of what we're replicating here. Does that answer your question? Not really.
Maybe I can add to that. So there is a context specific. So right now, we have the herbicide-resistant sorghum that's coming to the market. So for there, the concern is, are we going to get the resistance moving into Johnson grass? So you have a weed that is difficult to control.
So what is the pathway that you're concerned about? Reproductively speaking.
Through pollen.
But you look at that sort of in
Well, it can happen. So as Dr. Rooney was suggesting, it has implications on either side. When you have sorghum as a female, especially when the hybrid seed after seed is sitting on the roadside and it's segregating for male sterility. So in that case, sorghum is a female can get pollen from grass.
right? Because you could have plants that are predisposed to only 5%, up to say 5% hybrids. So, are you worried about that those plants being herbicide resilient?
Yes, in production
And
fields.
are they likely to be fertile?
There will also be other concerns, even if they are not herbicide tolerant. To the F1 hybrids are necessarily more invasive, right? Are they more aggressive? Do they have more weedy characteristics? So that's something we are evaluating right now. So we will find out, especially we have tetraploid organisms, we have triploids, we have pentaploids. Is there any particular body type that is more persistent or more adaptive to the field conditions?
That sort of thing. So you're finding evidence of two-end gametes, right? So I did want to make a point on terminology. So you're going to give talks, right? And so I strongly recommend you say two-end gametes or two-end pollen or two-end female gametophytes, whatever you want, not unreduced, because there's no evidence that they're genetically not reduced. And what's very critical in terms of mention that quote triplet block is going to be the point, not whether or not they're genetically reduced or not. And there are more types of two-end gametes than reduced gametes. So the term unreduced connotes the idea that it's genetically not reduced. It has identical genotype to the parental plant. You want to be a little bit careful about that from a cytogenetic genetic standpoint.
I might have to ask you to tell me about that later, because I don't think I fully understand. I'll communicate. Holly?
So I know it's something you're gonna look at in the future, but just sort of, would you hypothesize that gene flow in the opposite direction would be at a comparable rate that you observe?
So that's a great question. And initially, when this project started, I remember asking Dr. Muthi, like, why are we not going in the opposite direction? It seemed kind of intuitive to me. But so I talked to Dr. Hodnett about that, and he has started doing some processes in the greenhouse, and he is not seeing the same amount of gene flow. We were lucky enough that we have male sterile bicolor, but it's a lot harder to find male sterile Johnson grass. So just doing that experiment itself is a lot more complicated. But in a simple answer, no, we would not expect to see the same level. Yes, sir.
So in terms of herbicide resistance, how much gene flow can be tolerated?
That's a great question. I don't know. I don't know that
No, it'll never be zero.
Well, it depends on the herbicide program, right? let's say the natural mutation rate for A-list is like 1 in a million, then we want this gene flow rates lower than the natural mutation rate. If it makes sense. So, like we have a whole field, maybe we have like a couple of plants here and there, maybe easy to manage with the different programs. But if the rate is 1% is like very high, in my opinion. But one every
You would
100
see 1% in a real field. You have it, it's possible.
Right, and also the fitness penalty has been shown, right? Let's say 0.001%. That is still, let's say 1 in 10,000 is still a high rate. But it is managed. It is a lot better than 1%.
So we've all seen Jurassic Park, where chaos theory is the word.
We'll have to wait and see.
Yeah.
Yes, I made a mistake, but do triploids and pentaploids survive after the first generation?
Yep. Yeah. So those hybrid nurseries that we have at the farm, there are pentaploids and triploids out there. We just overwintered the first round of them, and I don't think any of the triploids survived. So they can establish, but I don't think they overwintered. But the tetraploids are a lot more vigorous and a lot more meaty. So yeah, that's part of what we're starting to look at is what does hybrids look like and how well they establish and how well they can survive.
Can sorghum propagate in a vegetative level? Considering it's a perennial, right? It's a perennial, right? Can it propagate vegetatively?
Johnson grass produces rhizomes, but sorghum doesn't.
But you can use steadily propagate if you want. You can take down the cuttings and go from the actual buds.
It does produce like crown shoots, because that was what you were asking. So there's
So, a hypothetical question. So, the head of the sorghum checkoff program comes to you, they're sitting in the audience and say, okay, as a scientist, and it's kind of referring to what other people ask, do we have a potential problem? Should we encourage the companies to move forward with the herbicide technology? Is it going to be a management thing? I mean, you can't control trucks. I mean, how do you respond to that? Because I've been asked that question like for 5 years. Is there going to be a problem with gene flow? So as a scientist, without you answering, what do you think?
so yeah, I think that's a great question, and I kind of just hit the nail on the head why we're doing this, right? But yes, I do think it is a problem, which is why we're studying it. We want to see how much of a problem it is, right? How much gene flow are we expecting to see?
Okay, so now Justin says to you, so should the company stop working on it, or should they keep moving forward?
I don't think they should stop working on it because we have gene flow in other species. We've seen it happen before, and I mean there is no silver bullet to fighting weeds. And so if we can use this technology for a certain amount of time and then have to find something else, then that's what we have to do. I don't think we should discontinue, projects. Yeah.
So it's the take home message, like you are trying to develop a hybrid or like hybrid sorghum, the normal sorghum bicolor, with a reduced probability to cross with the Johnson grass, so that maybe that hybrid has been released, it has like 0.00 something percentage to cross with the Johnson grass in the field.
So my objective is not to develop hybrids at all. My objective was to see which parental backgrounds that are being used to develop hybrids are less likely to hybridize with Johnson grass in the future.
Let Great. I think we're running out of time. But, congratulations. But I do want to make one point, like